The same machine can rotate in two directions. In one direction, it's pumping. In the other direction, then it's turbining, generating electricity.
It's a tradition we must break if we're going to prevent catastrophic climate change. We can't continue to rely on coal, oil and natural gas for power generation. Renewable energy such as wind and solar is playing a greater role. More than 1/3 of global electricity comes from low-carbon sources. But how can we store this electricity without using giant batteries containing metals that can contaminate ecosystems? One way is to harness the power of another natural and sustainable source that enables flexible power generation.
I'm around 2,000 metres above sea level in the Alps of Switzerland. And in these mountains, they recently finished building a power plant that uses water, this water here, to not only generate electricity, but also to store energy. But to understand how this giant water battery works, I need to go hundreds of metres underground.
It's not your ordinary hydro station. It's a pumped storage hydro facility using renewable energy which is able to store energy when the wind doesn't blow and the sun doesn't shine. Before we go any further, let me explain just how this plant works. Nant de Drance is a net consumer of electricity. Its role is to store and generate again when needed. When solar and wind create more energy than required, that excess is sent to the plant and is used to pump water from the large Emerson reservoir up to the Vieux Emerson reservoir. So the energy is being stored as water, like a water battery in the upper lake. When there's a higher demand for electricity than is being generated among other renewable energy sources, water from the upper lake passes through the turbines of the Nant de Drance plant, generating electricity. The same water can be pumped and turbined back and forth between the two lakes depending on excess supply or extra demand. Hidden away in the village of Le Châtelain, near the border with France, is the entrance to the Nant de Drance. Robert Gleitz, the delegate of the board of directors, is waiting for me.
Good morning, Emma.
How are you?
I'm doing well this morning.
Very good.
Welcome in Châtelard, here in the middle of the Swiss Alps, where we are going to visit the Nant de Drance power plant today.
I'm having trouble sort of visualising where we're going.
Basically, let's look at the drawing.
Okay.
So right now we are here in Le Châtelard, so at the bottom of the tunnel, and then we are going to drive underground with the bus, and we can go to the heart of the power plant.
That blue bit is Emerson Reservoir. We'll be travelling underneath it.
How far is this?
It's a 5-kilometer tunnel.
Wow.
And most of the plant is underground. So basically from the outside you see nothing. If you look at these triangles, that's the start of the main tunnel. What I propose is we go, I would say, through this tunnel, we go up and we visit everything.
It sounds good to me. Now I just have to follow the map. Oh, that's not too bad. Hey. First chore of the day.
But safety first. The usual hard hat and fluoro ensemble, plus a GPS that will help them find me if I get lost in the tunnels.
So Big Brother is watching you.
I feel safer already. So Robert, we're going up, not down.
Yes, exactly. I mean, we started at the Châtelard around 1,200 meter altitude, and we are going in direction to the cavern. Cavern is around 1,700 meter high. So this 5-kilometer tunnel has been drilled by a drilling machine, a very long machine, 300 meters, and it took about 4 to 5 years to do this work.
Yes, you heard right. It took almost 5 years to create these tunnels using huge drills and explosives.
I mean, everything in Nant de Drance has, I would say, something big. I mean, everything is large and impressive.
So where are we at the moment?
We are just underneath the Emerson Lake. So we have 200 meters of rocks above us and then the water.
That's exciting.
Yeah.
That's exciting information. Don't worry, we're safe.
Hydro is one of the oldest and largest sources of renewable power. Emerson Lake was built for this purpose in 1975 and is used by other hydroelectric companies. Nant de Drance decided to build the plant here due to the two existing lakes being so close together and because they were able to build the pumping storage plant completely underground. We've been driving for 15 minutes to get to our destination.
Now we are approaching, I would say, the heart of the power plant.
I'm trying not to think about how deep I am underground.
Here you go.
Oh, and another tunnel.
It's taken 14 years to develop this new plant at a cost of $2.2 billion. And as we head deeper into the mountain, you can see why.
So here we are almost into the main cavern. And here you go.
Whoa!
Yeah, so that's the main machine cavern.
Wow.
So almost 200 meter long. So 2 football fields. It's 52 meter high and 32 meter wide.
With up to 650 workers on site at any one time, 1.7 million cubic metres of rock was excavated. There are 18 kilometres of tunnels, and the 2 vertical penstocks that connect the 2 reservoirs are 425 metres tall, which is 100 metres higher than the Eiffel Tower. In here are 6 turbines that do all the work.
The same machine can rotate in 2 directions. In one direction it's pumping, in the other direction then it's turbining, generating electricity. No, I mean it's very quick. I mean in 5 minutes we can go from full pumping to full turbining. 5 minutes, which is, I would say, very short compared to the need of the grid and so on, but it also from minus 900 to plus 900 megawatt, 1800 megawatts, so twice the output of a nuclear power plant. Wow. For the grid stability, it's an enormous asset. If you can react, I would say, in case of an issue on the grid and generate, I would say, so much power in so few minutes, then it's important for the grid.
900 megawatts is 10% of the average Swiss grid capacity.
If we use all the water from the upper lake and we turbine full power, then in 20 hours we have our lake which is empty. That's an Olympic swimming pool every 10 seconds.
Big numbers. They don't do small numbers here. Everything's big numbers.
I'm on a tour of the Nant de Drance, a pumped storage hydro facility. In this huge cavern, you can only see the top of the machines. The whole generator pump turbine tree extends down below our feet over 3 floors. The reason the cavern is so big is so a crane can lift these giant machines up to the top floor for maintenance.
So here we are at the top of the machine, now machine number 4. Here that's a place where we inject the excitation current to create the magnetic field of the rotor.
All electrical generators require excitation to create electrical energy. Regulated direct current is provided to the coils that produce the magnetic field needed to excite the motor or generator.
So we are just standing here next to this small part of the machine. And as you can see here, there is a lot of machinery underneath. Here you have the excitation, here you have the motor generator, the intermediate shaft, the turbine itself, and then the pipes, I would say, connecting to the lower legs.
This is just a tiny part of it. I didn't realize just how much is actually, in these, 1, 2, 3 floors down is the machinery.
Yeah. When we are turbining, the water, I would say, flows down from the upper lake, goes through these main pipes, through the turbine, making, I would say, the turbine, turning, and then flowing to the lower legs. When we are pumping, the water goes into the same pipe, but in the other direction. Here, the turbine is then turning clockwise, pushing the water up and going to the upper lake.
Next stop, level -2.
Oh, wow.
Obviously, the machine is in operation and we can hear it.
Yeah.
But also another sign is that the counterweight of these spherical valves are up. So it means the valve is open. The water can flow, I would say, through the valve and can go inside the turbine.
So the valve is open, the weights come up, and then when it's time to close the valve, the weights go down.
Yeah, exactly. So this shaft is what we see turning. This is the part which is connecting the motor generator, which is above us, to the turbine below our feet.
And it's going so fast. I can feel the wind
Yeah.
blowing.
This machine is rotating 420 rotations per minute. So the variable speed is one of the features of this machine. So it's improving the efficiency of the overall plant.
And is it quieter downstairs?
Yes, it's
Okay.
quieter. So let's go down to -4. So now we are at the very bottom part of the cavern.
Wow, it's a lot colder down here.
Yeah, it's a bit chilly because we're here at the refrigeration level. So that's where we have all the cooling systems to cool the machines.
Right. So all these pipes are all for cooling.
If you look at here, that's one of the examples.
Yeah.
That's a heat exchanger. Here we are getting water, I would say, inside the heat exchanger. It's going out on the other side. And then you have a secondary loop. And this loop is then sending the water through the generator. And because you know the generator has not 100% efficiency, so part of the energy is transformed into heat, and you need to evacuate this heat. That's the purpose of the cooling system. Let's have a look to the main valve.
Okay, look.
So we are now at the very bottom end of the cavern. Here, this main spherical valve is located underneath the turbine.
It's huge. That'd be a huge hydraulic arm. So
Yeah.
what's that connected to?
I mean, that's to move the valve. These valves open and close in a quarter of a turn.
Right.
So you have a big ball inside the valve. This ball has a hole in the middle. When the hole is vertical, then the water can flow through the valve. When the valve is turned a quarter of a turn, then it's blocking the water and then it's closing the path of the water.
We haven't seen it all yet, but it's time for a rest and to find out if the money spent has been worth it.
Thank you for the hot chocolate. And thank you for bringing me inside. So a couple more questions for you. Pumped storage power plants. Are we going to see more of them? I mean, we're going to have more electricity. People want to use more electricity and they want to use less fossil fuels. So is this one way to do that?
Yeah, in fact, I mean, we are in a transition. A couple of years ago, you had only very large plants, controllable, coal, gas, nuclear, and so on, hydro, and so on. Now you have a more and more intermittent renewables. So solar, wind, offshore and onshore. You have also other types of generation. And all these generation are more dispersed or more split into the network. Therefore, you have a larger need of controlling the grid. So basically, what you need more balancing tools as well as storage in order to ensure that the electricity, which is not born at the right time, is then valued and put at the right time during peak periods.
This is an investment in Switzerland's future, safeguarding the electricity supply. The plant delivers energy storage efficiency of 80%, which Robert says is a positive business case for the plant and shareholders.
So you need more electricity to pump uphill than you do to turbine down. So how do you make your money?
We have a team of what we call traders who are looking at the electricity tariffs. So they're looking if it's going up or down and so on. And what you have to understand is that when you have too much electricity on the grid, the tariff goes down. If you have peak demand, then the tariff goes up. So when you watch that, then you know exactly when you have to pump or to turbine. You pump at a low tariff, you turbine at a high tariff. And so basically you are bringing energy from a period where it's not so much valued to a period where it's really needed.
Time for more exploration. And it gets darker and wetter the closer we get to the top lake.
Oh, now that's a pipe.
Yeah, that's
and
really
that's
the
a pipe
pipe.
too.
Yeah. I mean, these are the two pipes which are feeding the power plant.
Yeah.
So here the water is coming from the Vieux-Émousson lake and is flowing here. Here in the middle, we have another valve,
Yeah.
a safety valve.
Oh.
It's a butterfly valve, which can be closed in case of issue down into the power plant, so we can stop the water. And we go on one of the control panel of the plants. So here we can really monitor what's happening. So on the top, you see the numbers 1 to 6, and you see green dots and red dots. The green dots means the machines are in turbine mode. Here we see that the machines 5 and 6 are each generating 130 megawatts. We see that machine 1 is also in operation, but in a special mode. And then turbine number 3, they are working on it. They are doing some tests. Now turbine number 4 is also starting. It's already at 70 megawatts.
Oh yeah, it's going up. It's going up. 69. And if it was pumping, would it still be green?
Yes, but instead of having a T in the middle of the dots, then you would have a P, like pump.
Well, that makes sense.
Yeah.
Yep, nothing gets past me. A short while later, we've finally reached the top of the mountain to see the Vieux Emerson Reservoir, which is around 1,000 meters up from where we drove into the plant entrance.
So now you will discover the Vieux Emerson Dam.
Look at all that concrete.
Yeah, I mean, that's also necessary to keep all the water behind it. I would say here, behind this wall, we have 25 million cubic meters of water. And that translates, I would say, in 18 gigawatt hour of electrical energy if we turbine the complete capacity of the lake.
Located over 2,200 metres above sea level, it was raised by 21.5 metres to double the capacity to 25 million cubic metres, which is equal to 18 million kilowatt hours of storage capacity, around the same capacity as 400,000 electric car batteries.
Is there a better view? Can we
Yes,
go up, or?
let's go up.
Okay.
Let's go to the top of the dam, and we'll have a nice view on both lakes.
Lovely. Oh. Whew. I'm feeling the altitude, Robert.
Yeah, but I mean, here we are at 2,225 meter elevation, so that's normal to feel the altitude. Over there, you have a nice view over the Swiss Alps.
It looks a little empty.
Yeah, as mentioned, we can vary the level of the lake quite fast.
Yeah.
If we turbine full speed, I mean full power, in 20 hours we can empty the lake. But we can also fill in the lake in 20 hours.
What you can't see below the water is what had to be put in place to pipe that amount of water between the reservoirs. In Emerson Reservoir, when the water was at a low level, concrete parts weighing 1,700 tonnes were built on the shore. When the water was high enough, water was flushed out and air was pumped in to make them easier to transport. A barge then transferred them 800 metres to the holes drilled into the mountain. A concrete slab had been prepared when the reservoir was empty. Positioning rods were then used to lower the parts into place. Similar water intakes were built at the bottom of the upper reservoir.
So if we look at the dam here, we look down at the dam below, the caverns that we've been into, is it worth it? Is it worth the 2.2 billion?
I mean, we don't know because we don't know how the electricity market is going to move into the future. But we have 80 years in front of us, 80 years of a concession. And during these 80 years, we are going to pump and turbine the water, create value, I would say, for electricity or through electricity business. And we hope that obviously, I mean, the 2.2 billion will be, I would say, paid back to the shareholders.
So you talk about this concession, 80-year concession. What does that mean?
Concession means we have the right to use the water here during 80 years.
While Nant de Drance has a far lower negative impact than fossil fuel plants on the environment and communities, the extracted 1.7 million cubic metres of rock must go somewhere.
Well, we can see all the little trees here that have started growing.
Luc Gendre is responsible for the environmental compensation measures of the power plant.
So look, this is all material from the mountain, these big slopes here.
Exactly, yeah.
God. And
compacted in different slides.
compacted
Everything
right
that's-
down so it doesn't shoot down the mountain.
For instance, yeah. And you can see that the different species are growing quite well. and without any intervention of our part.
Yeah.
So that means all the seeds were already in the soil itself that we put on the rocks.
Are you seeing success with the environmental measures you've done so far?
We can say that, yeah, exactly. And that's also recognized by the authorities and also by the NGO.
The work has been monitored by an advisory group, which includes the World Wildlife Fund and Pro Natura.
The whole portfolio is accompanied with an advisory group. And in this advisory group, we have the NGO. We have also the different authorities, federal, cantonal, and commune. And we have for sure Nant de Drance. That's it. And each project is discussed in this group. And they make an advice, and afterwards we submit a building permit application, and the authority is giving us a permit, and we can do afterwards.
In the past, would companies even bother with looking after the environment afterwards? Is this something that we know is more important, that people are concentrating on now?
Exactly, we have to, because in my opinion that living have an impact. So we have to be conscious of that, and we have to make something to correct that and to minimize the impact that we have on the nature, because nature is essential for us.
There's no one perfect renewable solution to generate and store electricity. Extreme weather events are occurring more frequently, including droughts, which means water management of multi-purpose reservoirs is vital. Pumped storage hydropower is a lower risk from drought, and diversified grids can adapt to provide a more stable network.
Well, Robert, we started in the daylight and now it's dark, so you must be exhausted. But I did have one last question, which was, what's the importance of this pumped storage plant, not only to the Swiss grid, but also to the European grid?
I mean, if I want to illustrate that, I just have to remember how the people were excited when they designed, when they constructed, when they commissioned this plan. All these people who are, most of them, experts into electricity generation, they understand why we need such a plant, because we are going to need more storage and more capacity to manage the grid. The intermittency of the new generation, the variability of the consumption is really pushing us into this need of more pumped storage power plants.
This is the future.
Yes, exactly. And we are here for a couple of decades. We have built this plant not for the next 5 years, not for the next 10 years, but for the next 80 years.